Yes?
Yep, rolling. Yep. Okay, you didn't yell
Hello.
rolling.
Hello, thank you for coming today. We are going to be talking about ground-to-cloud media transport integration standards and approaches. This is John Mayotte from Imagine Communications, and I'm Kieran Kunhya from Open Broadcast Systems. So what is ground? A very unfortunate and confusing name. Any improvements are always welcome to this name, but what does it kind of mean? Well, during the pandemic, we use the cloud in practically all aspects of our lives. The cloud can scale up compute-heavy services on demand, such as Zoom, cloud-hosted email, social media, Amazon, Netflix, etc. But television broadcast production was one of the areas that didn't use the cloud. It's still mainly on-premise, and nearly all to mid-high-end production is some variant of in-person. Cloud economics, the scale-up and scale-down, seems like a great alternative to having and paying for resources that stay idle most of the time. But there are a bunch of technical issues that are stopping this, and we're going to talk about these issues, and John's going to talk about how the GCCG working group in the Video Services Forum is going to solve these problems. But I've been doing cloud production, well, yes and no. There are single-vendor monolithic applications out there, such as Channel in the Box, cloud switches, that live in the cloud, but they're not a multi-vendor production environment. And there are also, there are also a bunch of proprietary transports out there, most notably NDI. Those are great, but they stifle innovation. They're proprietary. And so in order to get widespread adoption, we must have multi-vendor interoperation by standard APIs, appropriate to task picture quality levels, standards for ground, cloud, cloud, ground, and an agreed mechanism for building these workflows. What makes cloud production difficult? You must integrate with the ground both ways, and it must work into existing workflows and existing broadcast workflows, which we'll sort of talk about. They're not quite the same as web workflows. So things that are SDI, SD2110, satellite, cable, over the air. And these are quote unquote legacy workflows, but they have very well-defined timing models. SDI, 30, 40 years, 2110-21, VBV, all well-defined, all well understood. And without this timing model, you cannot actually integrate into the ground properly. So you have variable or undefined latency. This is one of the reasons, for example, your web stream is 20 to 30 seconds behind. Like, why do you hear your neighbors cheer for the goal before you've heard it? And that's because they don't have a timing model. They just pick or guess a buffer that's massive or big enough and just deal with that. Intercutting the ground and cloud is also one of the big issues. If you cut between cameras, this variable latency is bad. You don't want to see a goal again. You don't want to see a car overtake another car again. You need to have a timing model to keep these feeds in sync. And that includes ground to cloud. Well, I'll just do 2110 in the cloud, right? People claim to be doing that. In a general purpose public cloud, this isn't possible right now. There's no full implementation of PTP in the cloud, and each cloud handles time in its own way. Cloud networks are shared by definition. They have packet loss. You don't really have full access in most clouds to network card capabilities like packet pacing for 2110. And is this even a good idea? Probably not. We don't want to have linear lockstep processing in the cloud anymore. We want cloud instances to be able to process faster and maybe a bit slower from time to time than real time, as long as we know the worst case, and that worst case is bounded. And how do we handle synthetic sources such as clips and graphics that are played out from the cloud? Another technical challenge. But in order to do this, we need to use cloud vendor-specific transport. So we have to trust the cloud. We have to sort of trust them to do transport their way. So this is the key things, I guess, so throughput and reliability. So all my data arrives and arrives correctly. And latency, so all my data arrives on time. So in the US, that's within 33 milliseconds. And the big data world, so the people doing fluid dynamics, doing AI, they have similar needs for large data transfers. But the cloud provider may not provide the internals of how this protocol works. It could be a black box. And one of the examples of such these is Amazon's Secure Reliable Datagram. So it's a sort of bulk transfer protocol. And that's the protocol used inside Amazon CDI, but you don't really know, they don't really explain the underlyings of how it works. I think Thomas Edwards and Toe have sort of talked about it, but they've hand-waved away the specifics. But in some ways, it doesn't really matter. And how does CDI sort of compare? It handles many of the challenges discussed. It's an agreed way of exchanging content between Amazon Cloud instances, pixel structures, metadata are all defined. And they guarantee throughput, reliability, and they bound latency, which is a key thing. This is a big step forward for the industry. But what is GCCG doing to help? Well, it's adding this timing model that I talked about. And what GCCG could do one day is leverage CDI for its applications where available in Amazon. And there could be others, Google could have their transfer protocol, Azure, et cetera, et cetera. So what is the VSF Ground-to-Cloud Working Group? What are they doing? Well, we are addressing these set of problems. And personally, I think the last difficult problem in broadcast production is how do I do a complex multi-channel production in the cloud and have comparable, it won't be the same latency as on-premises because it's laws of physics, and get it to the viewer. Numerous technical challenges that we'll sort of cover. John will certainly cover many of them. And you can find out more on this URL here. There's also orchestration and control, which we haven't talked about, the boring but important part. How do cloud and ground instances expose their capabilities? Is there an orchestration layer that connects everything together? How do we handle changes in signal flow? Resolutions change, frame rates change, audio channels change. How does an instance advertise that it's ready? And control of the flows themselves from ground to cloud and cloud to ground. And so John's next will be talking about the operating point.
Thank you, Kieran. So the VSF, the Video Services Forum, has taken on challenges like this in the past. The original work of the VSF was actually about helping broadcast customers interact with telecom carriers in a way that they could make flows go, originally analog television flows, go from one broadcaster to another in a well-defined workflow. So this really is in our wheelhouse. It's just a very modern thing. The first thing we looked at in studying this problem of how do we create the standards, the set of standards and practices that would let you build cloud-based workflows in a multi-vendor interoperable way, was to look at what are people doing today? What are the operating points of specifically the signals going to and from the cloud? So he said, well, look, there's certainly a set of people doing bandwidth optimized, low rate, think about watching TV and you see an interview that comes in over, say, Zoom, right? It looks okay and it comes in, there's not much timing model to it, but it's very low, the latency could be quite long, and you can sense that when the people being interviewed over Zoom, the latency can cause some challenges with the human factors. Equally, there's certainly interactive latency applications that can be engineered using H.264 with short GOPS and limited buffers and using the toolkit that we've always had as an industry, but we have to choose to use it. And there's a lot of applications that do that. NDI is sort of in that ballpark, for example. And then there's the notion of a premium compressed using something like JPEG XS to send a very low latency, very high quality contribution to and potentially back from the cloud. So these were kind of the three operating points that people tended to do work at today. We looked at, okay, what standards really define these? Well, this is kind of, the generic long GOP H.264 is pretty much the table stakes there. There's also some proprietary transports in this low end. This middle ground is pretty well covered, again, with H.264 and MPEG-2 and the sort of world of those codecs, although the connection management is a no man's land of ways. And then the high end was really kind of ill-defined at the beginning of this work. So in parallel with the Ground Cloud Working Group, the Video Services Forum took on creating standards for this high end. So during the time period we've been talking about, we rolled out VSF TR08, which defines how to do JPEG XS over SMPTE 2110 in an interoperable way. And there have been interop events and people have plugged their codecs together, and it's been very successful at doing multi-vendor stream exchange. Similarly, we rolled out TR07, which is a similar idea but uses transport streams instead of 2110 style packing. Just two ways of eating the same candy bar. They're really not that different. Then there's also VSF TR09, which evolved in parallel with this to address the connection management and security aspect of how to build a secure connection, how to advertise what could be taken, both for ground to cloud and frankly, even for inter-entity exchange on the ground. That's a big use case for TR09. How would I send a feed to Thomas, for example, if he needed a copy of the feed I have? Well, there ought to be a way, you'd think, but there isn't, except TR09 describes that way, and that's a new work that the VSF has done lately. So when you talk about inside the cloud, assuming this covers how do you get to the cloud, how do you get home from the cloud, what about inside the cloud? Because a lot of the things that happen in the cloud today are just a big monolithic application that you jam up there and you shoot video to it and you take video back from it, but it's really just one blob in the cloud. Well, that didn't scale. Suppose you wanted to have an application that instead had graphics and switchers and replay and a bunch of different interacting entities within the cloud. Well, you have to define what are the points of interoperability, what are the ways you hand signals off, both in space, meaning what is the codec, and also in time. So in space, you wind up saying, okay, the interoperability point, instead of it being at the IP packet layer, is at some kind of API in the middle where you hand off a buffer full of pixels and it shows up at the next guy in line. And that interoperability point is perfectly valid, and that's what we're defining in the GCCG group, is saying, look, let's define down to a certain layer and then assume that within each cloud provider or each hosting environment, there is some cloud provider specific mechanism that's going to carry the package from one entity to the next. And that work is going on. So in Amazon, this is typically CDI. In other cloud providers, it's other mechanisms. But it can be done in a way that the application works down to a certain level of API, and then it's picked up by local method after that. So that answers the how do you hand off packages, but the timing model is the key. If you think about traditional television, we used to time everything in the plant down to the picosecond to do analog. Nobody remembers analog, but apparently it's quite tedious to do it. Even in an SDI plant today, there's a big frame sync pulse that goes around and everything in the plant runs in lockstep. Everything in the plant, every 33 milliseconds goes thunk, and the next frame starts. Well, that's served us well for 40 years. We could keep doing it, but the reality of the way that the workflows work in pure compute environments, if we can give them a little bit of timing flexibility, we can get a lot of performance gain out of these applications. So the idea is to, instead of saying everything shall run in exact intervals of time, to have a timing model that embraces and manages the variability. So that's what we've been doing here, is really thinking about how do those things work. So to get there, we had to do a couple things. One is we said, well, look, there's a premium compressed case, TR07, TR08, TR09, those things are published. That work is done. The H.264 case, the only thing that's really not done well there is some kind of connection management methodology. TR09 is a good step, but it requires something in NMOS. So in AMWA, there's now work going on to define connection management for NMOS, for transport streams. And then inside the cloud, this time model is the big missing step. How do we manage time better? And then, of course, what are the blobs that we transport? That there's actually a pretty well-defined proposition in the CDI documentation, and it's available. Anybody could use it, and it seems reasonable. So all to say, this time floatingness, being able to allow some variability in the handoffs is important, right? We don't have to run everything in lockstep. Similarly, you have to be able to reconcile when you have this, you build up variability through the cloud workflow. At some point, you have to undo it because people, in the end, television is consumed by people. People expect to see the frames come at them in a very linear pace. If you mess with that, you create problems. In between, you could do anything. So that's the idea, is that in between, we're going to manage the variability so that at the end, we can turn it back into a linear presentation with the minimum amount of buffering. Because right now, the OTT world, we just throw buffers at things. And that's why your OTT stream is 30, 40, 50, 60 seconds late compared to your traditional delivery. But we could do a lot better just by keeping track of the thing. That's the idea. So we've established some vocabulary about how to talk about timing, and ultimately established some specs that we can use to capture the numbers, capture the arithmetic of keeping track of latency and variability. And it's a compound model, so we count the time that it takes to transfer the data, we also count the variability, and we come up for every workflow step with what's the minimum amount of time that it takes to get through that step, and what's the amount of variability between that and the sort of 99.9% maximum. And by being able to compose those, to mathematically add them up through a pipeline, we can figure out the worst case variability and worst case latency of that sequence of operations. And it sounds simple, and it's not super complicated, but it does take a fair bit of writing it down well, and that's the work of the committee these days, is actually writing down that timing model in a way that everybody who reads it kind of understands it the same way. That is a unique challenge, by the way, of people across the world in different languages, to write something down in a way that everybody who reads it understands the same meaning from it. So participation is welcome in these committees, by the way. People are welcome to join, and the more different people we have from different understandings and different industries, it's very helpful. So where are we at? Well, where we're at, we have some agreements. So for the ground-to-cloud link and the cloud-to-ground link, Tier 7 and 8 and 9 are a good set of standards. They're written down. People understand them, are starting to be implemented. Tier 7 and 8 are implemented by a lot of vendors. Tier 9 is relatively new. Similarly, H.264 and 265, they're widely used. We don't have to write anything new down for those. For going between instances, there's two things. We need ways to identify senders and receivers, some NMOS-like scheme. Guess what? We're working on that. We need a way to initiate connections, again, the ISO 5 equivalent, because that's, works on the ground, it'll work in the cloud. It's a perfectly good API. It just needs the right extra pieces to work in the cloud environment. And then, of course, what's the format of the buffers and what's the timing model? Those are all the things we're working on. Now, where do we go from here? Well, so we have work in progress documents. We meet every week, although we're not meeting this week because we're all here. And AMWA is doing the extensions of NMOS into these other areas, particularly in transport stream. The VSF is going to suggest the NMOS extensions for CDI. And then AMWA is also working on the transport stream in particular definitions. So there's going to be a lot of talks this week about a lot of these topics in detail. There's probably a detailed talk about Tier 09 at some point. There's certainly talks about JPEG XS. So pick the ones you want to hear about. Come back and join us. We're happy to see you. And where you can find Kieran over at his stand at OBS, Open Broadcast Systems. And I'm from Imagine, and our stand is right over there. Are there any questions about this work?
Any questions?
Are those chairs cozy?
Would you stay here for another hour or two?
Someone's on after us.
True. Are you guys having a meetup?
Not on this. Rainer and I are having a meetup on the SMPTE timing stuff, but that's another, I'm not even sure when it is. It's Tuesday, I think, Tuesday afternoon. All right, so I think we've rolled. So thank you all. Pleasure to hear you. And if you have questions, you know where to find us. I'm John, that's Kieran. Okay.
Thank you, guys. That was great.
Thank you. Have a great show.
It's going okay.
Yeah. Well, you're halfway, halfway into the first day. It's not
There you
even
go.
Monday yet.
I know,
That's
I
the
know.
way I keep thinking about it.
And I lost my glasses.
You lost your actual CA glasses?
Yeah,
You're
but
wearing them. I've done that. I'm laughing with you.
all right.
I think there's actually a comment in the document that says I mean, it's like we have all the definitions, all the